Hi everyone, this is John Wen. Today is June 24th, 2020. In today's video, I'm gonna briefly go through my updated progress item in research item since the past week. So you can see from the Gantt progress bar, here we have two to-do list items. For the first one, to extend the survey to the general version, the estimated progress since the past week is about 5%. And the second item, the deep learning workflow, the same estimated progress is about 5% as well. So let's look at the first item. It's about deep learning workflow. As we discussed in the last 2 weeks, we are going to adopt the second path, which is going to develop a GPU-based deep learning workflow in the data view, and which we are going to use CUDA and GNI directly. In the past week, I keep spending amount of time in the learning process, especially on the CUDA C and CUDA C++, and which I covered the warp divergency and synchronization and occupation, as well as the profiling. And today, maybe in the video, I can show you two programs which are cover the synchronization as well as the profiling. So let's get into the Visual Studio Code. For here, we have a program which is called a sum array with arguments. So this is a little bit different from the last time we showed the sum array, which is basically adding two very large array by the GPU. But this time, not only we are adding two arrays, we are able to have some manual input arguments in the main method. So you can see we have several arguments potentially can be input to the command line, which is basically first one to define whether the kernel is 1D or 2D. And then the input size. Keep in mind all the values are based on 2 to the power of something. So for example, if I have the input size 25, that means we have the input size is 2 to the power of 25. And then if it is 2D kernel array, 2D kernel grade, how many blocks we need to have for the x dimension that is specified in the third arguments. Also, we are specifying how many threads in the x or y dimension from the fourth and fifth arguments. So this is how the slightly change from the last time. But the goal, the purpose is still to running the array summation. So if you take a look at the code, we can firstly compile the code. You can see we compile the sum array with the arguments CU, and the output file is a profiling test.out. And basically we are including a common.object. This is a compile file of the common.h and common.cpp, the header file, because we declare some functions in the header file and we implemented them in the CPP file. So we need to include the compile file of these two in the compilation of this CUDA file as well. So when we compile this one, we will get then compiled file from the NVCC, and then we can do the profiling. The profiling is also called the performance analysis, which is enable us to estimate or to check what kind of efficiency will be realized by different kind of hyperparameter we set into the implementation or running the kernel. So for example, let's say we are going to run the MP provisioning, and then we check the matrix, which is a global memory load efficiency, as well as a streaming multiprocessor efficiency, and achieved occupancy profiling test on this file. And we have arguments 0, 25, 0, 7. That means we have one dimension grade, and we have 2 to the power of 25 size of input data. which will be randomly initialized. And then because we have 1D, a third argument we don't need to care. And also we have 1D, we only need to specify how many threads we have in the x dimension in each thread block. And here is 2 to the 7, that means we have 128 thread in the x dimension of the thread block. So if we run this one, we are going to get the efficiency. You can see the global memory load efficiency is about 100%, and the streaming multiprocessor efficiency is about 87%. And also we have achieved occupancy, and occupancy is defined by the active warps divided by maximum warps a streaming processor can have. So that means how many active warps is existing in a streaming multiprocessor, which is very important because sometimes we have the latency, and in order to hide that latency, we need to have enough number of active warps in a streaming multiprocessor. So that's a key how we do that. And also we can try another combination, which is a two-dimension grid, and we have the same size of data input, and we have in the x dimension we have 2 to the 20 threads for the x dimension in the grid, and then we have 2 to the power of 5 in the y dimension, because these two you can divide the y dimension can be derived by dividing the 2 to the power of 25 divided by the 2 to the power of 20. And the same, we have the x dimension, we have 2 to the power of 7, and y dimension we have 2 to the power of 2. So let's see the performance, how it works. So you can see the streaming multiprocessor efficiency is much higher than the first one. Also, the achieved occupancy, this one is a little bit lower than the first one. So for most of case, we can analyze whether we want to achieve a better efficiency or the occupancy. And of course, we have more matrix can be checked by the NP provisioning tool, and that is help us to analyze or improve the performance. And this is something we may be able to do in the data view in the future. And when we are executing the code in the GPU, we also can do the compiling and then do the profiling, and see what kind of hyperparameter can give us a better performance, and then we can use that to do the execution. So this is one thing we can think about. A second thing about I think that's interesting to know is the synchronization. Not only we can synchronize between the host and the device, and we can also synchronize within a thread block. Here is one example, because we are doing aggregation in this example. Basically, it's a kind of reduction problem. We are going to adding array into one single element or one single result. That means we have to do the parallel adding, and the result will be one single output. So this is an aggregation issue, and because of that, think about if we want to add 3 items together sequentially. Maybe we add the first one and second one, and then the third one will be added based on the output of the first 2, right? But if we do in parallel, how can we ensure that the third one is always added based on the output of first 2? And maybe it can be a little bit faster, and before first 2 output the result, the third one is already added something, right? So we have to do the synchronization, especially for this for loop. And every time a warp is going to execute this code, and because it's a kind of divergency, make sure we have the 32 threads in every warp to execute this for loop. And then by the end of every iteration, we are going to do a synchronization within this block, or within this warp, and to make sure by the beginning of next iteration, the result has already been summed, and there is no halfway result, or there is no result that is not completed when we started the next round. So that is something very interesting. And also I prepare slides. I think it's better to illustrate better to show you the how this code is working. Basically, this is done by, maybe we have the 32, for example, we have 8 threads here, but we can imagine we have 32 threads in a block, and then we divide by 2, that is the offset we're going to have. And for every thread, consecutive thread, we're going to access the thread ID, which is correspond to the index of the array we're going to access. And then we plus this offset, which is a half size of the block size, and that means we can access, maybe here is this 3 and 4, we're going to add them together, and 5 and 7. So in that way, we always add the first item, and then the second item is offset distance away from this current index. So you can see we can add in this way, and by several rounds later, we're going to get the result at the beginning of the array. So this is how the GPU is going to implement this kind of aggregation. But this is only one way. There are multiple ways can be implemented, and that's kind of algorithm we can adopt. And this is the first item, and second item is to extend the survey to the general version. And the progress since last week, I carefully read the WRPS paper, and I refine the explanation as well as the pseudocode of the WRPS algorithm in the journal version paper. So I think right now it's in a much better shape, and I think the pseudocode looks a little bit better as well. But I'm not sure if that's compact enough, because I try my best to make the words brief or compact enough, but I think there still take some place. So I hope Dr. Liu or Dr. Che maybe help to take a look and see if there's anything further we can do. And further, I migrated the journal version paper to the ACM journal format. So currently it's already available on the Overleaf, I believe. So if we take a look here, so here is AMC. Also, I added a content list in the front page in order to make it more clear. So this is all the content migrated from the existing one. So we also have the pseudocodes already in this version. So furthermore, I think we are able to modify based on this one. So I think that's pretty much for today's video, and I think, yeah, that's it for today's video. Thank you so much for your time. Hope you can enjoy this video, and until next time, happy coding.